I don't know if you've had a day like I've had. I went out this morning and I had to get past 3 different accidents. People just not driving like they should. Ju- Just to get back to so I could come to work. All righty. So for starters, it looks like almost everybody's here. For starters, I'm reminding you that we are doing the 9-week exam on Tuesday. You check your schedule on your homepage. You should see the exam schedule. So the one for 6th period is scheduled for Tuesday. Wednesday we'll do some other down activities, but those won't be tested. Actually, because it's AP, we will go on, but they won't count until next term. So just keep that in mind. But again, the AP exam is going to be in the AP classroom. So I know we don't have any trouble with y'all. Everybody can log into that. If you haven't already gotten in touch with Miss Martin, she needs to know if you are going to take the AP exam, keeping also in mind that for you all, if this is your only, you have 2 STEM classes, math and sciences, and if you are not doing math, then this exam would be free. So I would try it if this is your only STEM exam, or if you have to make a choice. Uh, that's up to you. But if this is your only STEM class, then I would go ahead and take advantage of the fact that you can take this exam for free and won't have to pay for it. So keep that in mind. You do have to let her know soon. There's an application that has to be submitted, and you have to everybody has to let her know yes or no. So you do have to say, I decline or I intend to take the exam. So make sure that you get in touch with her about that. That's not something you send to me. Okay. Looking at the tests, I did want to just stop on 1.9 and 1.10 because they talk about trophic levels and energy levels, and we've talked about productivity. So I'm just going to show this one today. I think everybody's here. And we will do that. This will be the last new thing for this 9 weeks. And then we'll leave food chains and food webs for when we come back. But this talks about the 10% rule is kind of an important thing. So we need to make sure that you talk about that. And we've already talked about trophic levels in when we looked at the pyramid and productivity and looking at the pyramid. So this kind of loops in with that. So I did want to make sure that we covered this before the exam.
In 1.10, which are trophic levels, and the 10% rule. So we'll be talking about how energy flows through ecosystems and how the available energy decreases as we move up the trophic pyramid. We're combining 2 different topics here today, so we have 2 different objectives and 2 skills to practice. The first objective is to be able to explain how energy and matter flow through trophic levels. And the second objective is to be able to determine how energy decreases as it flows through an ecosystem. The 2 skills we'll practice at the end of today's video are explaining an environmental concept or process and then calculating an accurate answer with units. So we will be doing some math at the end of this video. So before we talk about how energy flows through ecosystems, we have to establish the conservation of both matter and energy. So very important to remember that matter is never created or destroyed, it only changes forms. This is key to understanding how both matter and energy flow through ecosystems. So let's
From
Wow,
idea to submission,
that's quick.
empower students to do their best work with Grammarly's comprehensive AI writing assistance.
All
let's
right.
take a look at an example.
This is called the law of conservation of energy. Okay, so this is actually a law. Matter and energy are law of conservation of matter and energy. They say the same thing, that it is never created nor destroyed, only changes forms. That means it's recycling. So we've been talking about recycling all these past couple of weeks. It goes with the law of matter and energy.
When a tree dies, the tree will get decomposed, and we may not see the tree physically anymore, but all of its matter was conserved. So the carbon, the nitrogen, the water, and the phosphorus within the tree were all returned to either the soil or the atmosphere, or went into the bodies of decomposers. And so we did not actually lose any of the matter. It looks different, but it still exists, and it's just transformed into a different state. Let's talk about this with regard to energy as well. So if we look at photosynthesis, we have the sun's rays, which represent light energy, and they're going to be converted into chemical energy by the plant, and that's glucose. So if we look at the diagram and we were to actually count up all of the atoms involved in that process, we'd see that all of the carbon, oxygen, and hydrogen entering the plant as carbon dioxide and as water flowing from the soil are all going to be conserved either as glucose or as oxygen that leaves the plant's leaves during photosynthesis. So photosynthesis helps us kind of grasp here the conservation of matter, but also the conservation of energy, because we have the sun's rays that hit the leaf. That's a form of energy. But once those rays hit the leaf, they're not destroyed. They're just transformed into glucose, which again is chemical energy. So photosynthesis is a really helpful way to remember both the conservation of matter and energy. We have a fancy name for this. It's called the first law of thermodynamics. And
All right, I did want to also say that that's something that you'll cover in chemistry called balancing equations goes with this law. And just a quick look, where the carbon, you see 6, all those numbers in front, 6 CO2. So there's 6 carbons and 6 oxygen, 6 O2 molecules. And then you notice on the other side on the red, you got 6 O2 molecules. And in the glucose, you have 6 carbons. So again, conservation, they change places, they change partners, we like to say. But it doesn't really get destroyed. It looks like something else, and it just keeps recycling. When this sugar gets used up, we break down this sugar into separate carbon. The plant decays, and that carbon goes right back into the atmosphere and starts all over again. So again, first law of thermodynamics, another law that you got to remember.
that's just a reminder that energy is never created or destroyed. It's just transformed into a different form. Biogeochemical cycles that we've spent the last couple days on, so the water cycle, carbon cycle, nitrogen and phosphorus cycles, those all demonstrate that there's conservation of matter. So again, when an animal dies, the nitrogen in its body is never destroyed, it's just transformed. It goes through ammonification, returns to the soil as ammonia, and then can be used for plant growth in the future. Food webs, which we'll focus on today and tomorrow, are how we demonstrate the conservation of energy. So we talked about the conservation of energy with photosynthesis, but let's look at it with an animal here. So let's imagine that a rabbit is going to eat the leaf that produced that sugar through photosynthesis. So the leaf is no longer there, but the energy in the leaf has been transferred to the rabbit. The glucose in the leaf is going to be broken down by the rabbit's body. It's going to fuel growth of the rabbit. So some of it might be converted into muscle or fat tissue within the rabbit. Some of it might go to fuel the rabbit's movement. So the energy is conserved. It's never destroyed, even though the leaf was eaten by the rabbit.
We have got to the point where literally anybody can build a fully working app without knowing how to code. This is base.
Now we'll talk about what happens to energy as it transfers between trophic levels. So each time energy transfers from one form to another, some of it is lost as heat. Now it's not destroyed, but it's just given off to the surrounding environment, and it's no longer useful energy that can be used by organisms. And so we'll talk about what that means here in a second. So let's take a look at an example with electricity generation. If we have this coal-fired power plant here, and all of the potential energy in the bonds of that coal are released and converted into electricity, only about 35% of the energy that was in the coal is going to actually make it to electricity. The other 65% is going to be lost as heat while the coal is being burned. Then, as that electricity is flowing down transmission wires, another 10% or so is going to be lost, and only about 90% of the electricity is going to actually make it into your home. Then when you turn on a light bulb, 95% of the energy flowing into the light bulb is lost as heat, meaning only 5% is coming through as actual light energy. So what this demonstrates is each time we transfer energy from one form to another, so from chemical energy in coal to electrical energy to light energy, we're losing some of it as heat. Now we can think about what this means as it applies to ecosystems. So each time energy is transferred from one organism to another, the amount of available energy is decreasing. And that's because the organism that was just eaten had used up most of the energy for things like movement, development, and just cellular respiration, fueling all of the processes its body needs in order to survive. So we can look at an example here with an ecosystem. If we have 1,000 joules of light energy that the producers are receiving, remember they're going to need to use 90% of that. So they're going to use 990 joules for their growth, for their metabolism, all of those things, and only about 10 joules are going to be available to the elk. When the elk eats the grass, it gets those 10 joules of energy, but then it's going to use up 9 of those joules for, again, development, cellular respiration, and it's going to be lost as heat to the atmosphere. Then when the lion eats the elk, and I don't know what kind of ecosystem we're in here where a lion eats elk, but it's just a helpful diagram, it's only going to get that 1 joule of energy. So that means that each time the energy transfers from one organism to another, only 10% of the energy is making it to that next organism.
I wanted to stop there with the picture. All right. And a lot of times students have a lot of trouble with this concept of the fact that it's taking in a certain amount. So this is where the math is going to come in. They're going to always give you how much energy. And then you see this word joules. The unit for energy is joules. And I don't think he's mentioned that so far. But if you were in physical science, you might have heard that word joules before. And everything has anytime you're measuring something, it has a unit. So the metric unit for energy is the joule. And they're always going to give you how much energy it started with and expect you to understand that the organism that absorbed it in the first place is getting 100% of the energy from the sun. So say that when we say 100%, that 1,000 is 100% of the energy that plant absorbed. And then, because it is a living thing, all its activities require energy. So it uses the energy. So that by the time the elk eats the plant, it's only getting what is stored and that the plant is not using, which is only 10%. It uses 90%. So they have calculated that each organism in a food chain uses 90% of the energy that it takes in, and it only leaves 10% left over for the next level. So that's why it dropped by 10% from, and actually that should have been 100, but it should have dropped from 1,000 to 100 to 10. And then the 10 went to 10% of that is 1, and 10% of that is 0.1. So yeah, somewhere okay, they had 1,000 is lost to the environment. Okay, there we go. That's a lot of energy lost to the environment. Okay.
Energy transfers from one organism to another, only 10% of the energy is making it to that next organism. So because the amount of available energy decreases with each step you go up the trophic level, we use a pyramid shape to represent this. And trophic just means growth or nourishment, so that's a helpful way to remember what a trophic level is. And so because there's the most energy available at the base, it's going to be the widest. And then each level up is going to get a little bit more narrow because there's less available energy at that level. Remember, we didn't actually destroy energy. It was used up by the organism, so it was lost as heat as they move around, or it was used up in cellular respiration. But only about 10% of it is going to transfer on to the next level. And so we have a handy rule to remember this, and we call it the 10% rule. 10% rule just reminds us that only about 10% of the energy from one trophic level makes it to the next. The other 90% is lost as heat, while the organism uses that energy for all the processes it needs to fuel.
This is what Ivy League universities you can get into with a 3.6 GPA.
90%.
So if we take a look at this diagram, we can kind of see that represented here. From the producers, only about 10% of the energy is going to move on to the rabbits, who are the first level to consume the grass. 90% will be lost as heat. Then onto the snakes, another 10%, 90% loss as heat, and the same thing for the top predator here. Now we'll talk about the names for each trophic level, as well as how the 10% rule also applies to biomass. So at the level, as well as onto the snakes, another 10%.
I wanted to pause it there. This is where folks get confused as well, because it's going to be 10% for each level, but they're going to ask you to calculate. So it won't be enough for you to say 10% each time. And then you always have to remember that 90% is lost, but then they might ask you to calculate what is the 90%. What is 90% of whatever number they give you? So that's the number that they would give you in the question, and you would have to calculate that.
90% loss is heat, and the same thing for the top predator here. Now we'll talk about the names for each trophic level, as well as how the 10% rule also applies to biomass. So at the bottom, we have the producers. These are the plants, and they form the base since they are going to produce the usable energy in every ecosystem. Remember though, they're not really making the energy, they're just converting light energy into chemical energy in the form of glucose. The next level is the primary consumer level, and these are the animals that are eating the plants to get their energy, and we call them herbivores. Then we have the secondary consumer level. These are animals that are going to eat primary consumers, and so we call these either carnivores or omnivores, because sometimes these secondary consumers also eat from the producer level. So this example here of a blue jay eats some animals, but it also eats some plants. Same thing with the raccoon, and so we call those omnivores, and they can belong to two different trophic levels. Then finally, we have the tertiary consumers, and these are our top or our apex predators. So these are organisms that are going to feed on secondary consumers. Now we'll talk about the 10% rule as it applies to biomass. So because energy is needed for growth, and only 10% of the energy from one trophic level makes it onto the next, that also means that only about 10% of the biomass can be supported. Now, what is biomass? Biomass just refers to the total mass of all living things at a certain trophic level. And so if we were to look at this diagram here, at the base, we could support about 1,000 kilograms of producers. But since only about 10% of the energy moves on to the primary consumer level, that means we can only have about 10% of the biomass as well, since all biomass needs energy in order to be developed, to be grown. So we're only going to be able to support about 100 kilograms of primary consumers from that 1,000 kilograms of producers. Then that's going to decrease by 10% again, by 90%, excuse me. So we'll have 10 kilograms at the secondary consumer level. And finally, when we get to the top of the pyramid, there can only be 1 kilogram of tertiary consumer biomass for every 1,000 kilograms of producer biomass. So this is really important. I want to reiterate this. At the base, only 10% of that energy moves on to the primary consumer level, so only 10% of the biomass can be supported. So that's why when we look at a given ecosystem, there are far, far, far more plants than any of the animals in the ecosystem. And that's because you can only support 10% of the primary producers.
Those eyes, that nose, your hair, your neck.
That you had at the consumer level, same thing with the secondary consumers, and same thing with the tertiary consumers. So now we'll practice actually calculating the amount of energy available at different levels. So it's a really simple calculation. To calculate the energy available at the next trophic level up, you're just going to move the decimal spot one place to the left, or just divide by 10. So if we use this example where we have 95,000 joules at the producer level, we would just move that decimal place one spot to the left, or divide by 10, and that should give us 9,500 joules, roughly, that would be available to the primary producers. So what I want you to do is see if you can calculate the secondary producer level and the tertiary producer level.
So I am pausing, and you practice. Remember, you're just moving the decimal point over. And again, the decimal point represents, every decimal place represents 10%. 10%, I guess you want to say it that way. It's a base 10 system, so each spot is 10 times bigger or 10 times smaller. Say it that way. All right, so since we're just moving the decimal point, I'm assuming that it didn't take you long to figure that out.
So again, pretty simple. We're just moving the decimal place one spot to the left or dividing by 10. So at the secondary consumer level, we'd expect 950 joules and then only about 95 joules available at the tertiary consumer level.
All right, I wanted to say this too. He used the term apex consumer. That's a vocabulary word you need to know, and it's always referred to. An apex on anything is the top, and it's referred, so it can be a tertiary consumer is the apex consumer most of the time, unless there's another level, and there's seldom is, but that is also because whatever is at the top is also the apex consumer.
10% rule also applies to biomass. We can do the same type of calculation to determine how much biomass would be found at each level. So starting out with 80 kilograms at the secondary consumer, I want you to see if you can work both up and down the pyramid to figure out how much biomass would be supported at each of those levels. So again, we're just moving that decimal.
Give you a minute to write that down. Hopefully you are.
Place one spot to the left to figure out the tertiary consumers, which should only be 8 kilograms. But we're actually going to do the opposite and move the decimal place to the right as we go down the pyramid. So that would give us 800 kilograms at the primary consumer level and 8,000 kilograms at the primary producer level. So our practice FRQs for topics 1.9 and 1.10 today will be covering two different skills. One is explaining an environmental concept or process. The other is calculating an accurate answer with units.
Okay, so I'm going to just pause this here and let you work on it from here rather than me copying it and put. And I'm not. In other words, this is not for a grade. So go ahead and just work on this for practice, and then I'm going to open the those units in the AP classroom. So the first thing you're doing is explaining why a relatively large forest can only support a small number of wolves. So think about it in this way. If you were draw yourself a visual. I like visuals. Draw yourself a visual of a pyramid and think of where the wolves would be on a pyramid. What level would they be at? And then you can explain why, even though they live in the big forest with all that vegetation, why are they only going to be able to be supported by a small, why is that forest only going to be able to support a small number? All right, calculate the amount of energy available to a tertiary consumer in the following ecosystem. So they are giving you a number, and this is the base. Remember, these plants are your base of your pyramid. So again, if you have to draw yourself a pyramid, answer it that way. Okay. Or maybe I will put this in. Because I really do need you to practice. I don't need you to pretend like you're doing this. And sometimes y'all don't do stuff if people's not gonna grade it. All right, so everybody, for the next few minutes, everybody's working on this question. And remember that J stands for joules. And just like in math, if you were answering a question and you didn't write a J or write the word joules, then your answer can be partially wrong because we need to know what units you're working in. That J tells us we're talking about energy without you saying energy. All right, I'm going to stop sharing for a minute so that I can actually add this to your. That's a nicely colored. Stop talking. Okay, give me 1 second. All right, so this should be, okay, I'm glad I looked at that. Aha, I put the wrong dates in. Okay, now it should be on your to-do list. However, I don't see it. All right, it must be the date again. Today is the 26th. I saved it and now it's disappeared. Okay. All right, it took its sweet time about loading, but you should be able to see it now. Okay, on mine, I had to click see two more. So it should say FRQ 9.1 and 1.9 and 1.10 energy and ecosystems. All right, so if I'm sharing, let me view this as a student to make sure that you see what I see. And I still don't. I'll take some of these out. Sometimes there's too many things on the list. And there it is. That was the issue, is too many things on the list. All right. So it should be FRQ 9. Sorry, why do I keep saying that? 1.9 and 1.10 energy in an ecosystem. So that's the same one we were just looking at in the video. Asking said now. So again, what I'd like to see in your answer is a written explanation, and you can even include a pyramid or a visual explanation of why wolves, only a small number of wolves can be supported by a large forest. And then the second one, I want to see you actually write numbers and create an ecosystem where you're showing me all the available energy, starting from the bottom all the way up to our tertiary consumer. Okay, so this is not just a one word answer or a one number answer. You're going to show me, how did you get from 100,000 joules of energy that in the plant level, the primary, the producer level, to whatever number you're going to get when you get to the tertiary consumer. And again, if you simply draw a pyramid and put numbers in it, that'll be a good way to show your answer. Okay. All right. Other than that, I'm going to leave it at that. It's Friday. You have an exam on Tuesday. I would rather you spend the rest of the time going back looking at the previous units. If there are any questions about those units, I would love for you to ask. We are doing, again, a lot of stuff. A lot of stuff. Always know what is environmental science. Always know the scientific method. Scientific method means, because they use a scientific method for all observations and research. So make sure that you know that it starts with making an observation, and observation employs all 5 of your senses. And it's always a question. Number 1 is always a question. Or say number 2, after you've made your observation, ask the question, I wonder why this does what it does. Then number 3 on this one is the answer to your question, or what you believe the answer to be the question. It has to be stated in, it's a statement always, and it always has to be stated in the format of, if I do this, then this will happen. Or it's because you're trying to answer a question, so you're setting up a testable situation to answer the question. So it's always, if I do this, I expect this to happen. Then you conduct an experiment so that you can prove what you think. And then you collect data along the way. And remember, data can be numbers, it can be a chart, it can be pictures. And with environmental science, a lot of times it's pictures. And then based on your data, you come up with a conclusion. The conclusion always either supports your hypothesis or it rejects it. If it rejects it, the next step is to retest. So state a new hypothesis. Your question doesn't change. You're still trying to answer your question, but you want to come up with a new answer to the question, since the first one was not the answer to the question. Or if it proves, if your test proved your thoughts are right, that's the end of the experiment. But do make sure that you know the scientific method in order. So that is the order: observation, question, hypothesis, experiment, analyze, and conclusions. All right, that's module number 1. Okay, then we get to the real environmental stuff, which is relationships in an ecosystem. We looked at them as being plus and minus. Is this relationship good for you? Is it bad for you? So we need to make sure that you understand the vocabulary for these words. Okay. Mutualism is a plus plus situation. Commensalism is a plus, and they put 0 because they don't care. And parasitism is a plus minus. So you need to look at the relationships in those terms. Always know your vocabulary. Fundamental niche and realized niche. You need to know the difference between the two. Niche is what it does, where it lives. And then you can have other organisms in the same area doing different things. This one as well, vocabulary, intra-species and interspecies. So know those vocabulary words. In other words, always know the vocabulary. Always look at the unit, the module, and I always say look at the overview part of it so that you know what all the vocabulary is, and go through, look at your visual pictures for each of these cycles. Okay, carbon cycle, nitrogen, phosphorus, water. Look at the cycle itself and know all the steps and know all the words associated with all the steps. And then we're stopping here. So we're not doing the actual food chains and food webs yet. So we stopped here. Okay. So all of that information has the possibility of showing up on Tuesday's test. If there's a topic you have questions about, please ask. If there's an assignment that you need to turn in that you have not turned in, but you think is closed, I tried to go in and open most of them. Please ask me to open anything that is closed that you cannot submit your work. Late work is always better than a 0. I will look. Nitrogen cycle quiz. You mean the nitrogen cycle AP Classroom 1 point? Is that the one you're asking? Okay. Looks like I didn't give you anything. Let me check my. I didn't add anything. Nitrogen. Okay. All right, I fixed it. Thank you. Okay, just a couple of heads up things. Know your formula. Some of you actually had the question on the last FRQ that you did. Know how to calculate net and gross productivity. Know, what's the word I was looking for? Resource partitioning. That's a vocabulary word we used earlier. Resource partitioning. All right, there are a couple of food web questions on there, but they have to do with energy flow. So just remember that the producers are at the bottom. The arrows are important. They tell you the direction of flow. Okay, so the arrow is always going from the thing that is eating to the thing that is doing the eating. Okay, which way is the energy flowing? That's what the arrows represent. Okay, so I don't need to take those questions out because I think you can handle that. And then we might just skip doing that particular unit and move on. All right. And there's only one FRQ question, but it has parts to it. All righty. Any questions, folks? Any questions? You have no questions for me, and you feel like you're all caught up, and you're ready for this exam on Tuesday. Okay, then I will see you Tuesday. Have a wonderful weekend.